Greetings and welcome, pre-calculons. This is a video which is for you going to be nice and easy, I hope, because it's a review of a concept of simplifying complex numbers. And I do believe I have some other videos posted for my kind of Algebra 2 or Math 3 equivalent students, so you can feel free to look up those as well if you needed more practice or explanation. But we're just going to jump right into doing some problems. Complex numbers are numbers of the form a plus or minus bi. So they have a real part and an imaginary part. When they're in this form, it is called rectangular form. And a couple facts about I. I is defined as being the square root of negative 1. And we discovered a couple other properties that or facts. I squared is equal to negative 1. I cubed is equal to negative I, and I to the fourth is equal to 1. So, and any I to a power after that actually repeats in this pattern where it's I, negative I, 1, negative I, 1, and so on. So here's kind of our basic starting fact. So let's start by simplifying the following. Suppose I've got I to the 53rd power. Now, because I have this repeating pattern here, the most valuable of these, I would say, is the I to the fourth equals 1, because 1 is an awesome number, mathematically speaking, right? 1 times a number is itself, right? Something raised to the 1th is itself, and 1 is just the best number out of all of these, I would say. So I'm going to try to find a way, can I write I to the 53rd in terms of some number of I to the fourths? And so the way I ask it is I to the fourth fits into 53 how many times? And I believe it fits in 13 times. 4 times 13 would be 52, and I'd have a remainder of 1 left over. So just to clarify, this is mathematically equivalent to the left side there, because power to a power property would say I could multiply these. 4 times 13 is 52, and product of powers would say 52 plus 1 is 53. So it works out quite nicely. And why is this helpful? Well, because I can replace I to the fourth with 1. So I'd have I to the 13th times I to the 1. 1 to the 13th power is 1 of the benefits of 1 once again. So 1 times I to the first is just I. So I'm able to conveniently reduce this down to one of my original 4. And then one of the things we did not see in our previous course, what happens if I've got a negative exponent there? And you could do some manipulation. You might remember properties of negative exponents. You can move this down into the denominator, make its exponent positive, things like that. But it turns out I can actually still use the same trick, and it kind of works nicely because of I to the fourth equaling 1 again. Let's see, 4 times what is negative 13? 4 goes into negative 13. Well, I just realized I could say 4 goes into 13 negative 3 times, but then that would have a remainder of negative 1, which isn't the most helpful. But check this out. If I go a little bit further than that, 4 to the negative 4 is negative 16, right? And negative 16 plus 3 would be negative 13. So trying to write this with a positive exponent will be more helpful. I'll write it the other way as well in a moment, I think. So I to the fourth is 1, and 1 to the negative fourth times I to the third. 1 to the negative fourth is the same as dividing by 1, which isn't going to change my answer. I just happen to get I to the third. All right. Now, if I'd written it alternatively, like I said, I to the fourth all to the negative third, my remainder, this is negative 12. Negative 12 plus what is negative 13? That would be a negative 1. I would have gotten something like this. I to the negative 1, and this I would have to move downstairs perhaps, and then there'd be a little bit of confusion as to what to do, because I'd basically end up having 1 over I to the first, and somehow I to the first is equal to I to the third. but we'll get to that in a moment. It's easier to kind of go past the negative number to get 16 in this case, to get a positive exponent for my remainder. So that works out well. So that's kind of our first type of simplifying. Other things I can do with complex numbers is I can add them. So for instance, if I have 2 plus 3i, and I'm adding, say, 7 minus 2i. So here's two complex numbers that I'm adding, and in order to do so, all I have to do is add the corresponding parts. So 2 plus 7 is 9, and 3i plus negative 2i is just positive I. And that works out quite nicely. One of the interesting things about complex numbers is that addition or subtraction are not closed operations. And what that basically means is, notice this particular case, if I do 2 plus I, and let's say I don't know, subtract 5 plus I. So here's two complex numbers, members of the imaginary number set. And if I subtract these, I'd have 2 minus 5 is negative 3. And then I minus I would be 0i, which is 0, and I get negative 3. So notice it's actually possible in some cases to add or subtract complex numbers and end up with a real number, which is kind of weird. So in terms of number sets, that's called kind of an open operation, that it's possible that I could add these two things and get a number that isn't even in the original set. It's kind of an unusual case. For multiplying, it's not that difficult either. 3 plus, say, 2i times, let's make things a little bit peculiar. What if I've got negative 4 minus I times the square root of 5, just to make things a little ugly for us. So if I'm multiplying two complex numbers, all I'm going to do is FOIL it out or double distribute. So I'll multiply the first term by both of those and the last term here by both of those. And let's see what I end up with. So 3 times negative 4 is negative 12. 3 times negative I roots of 5 would be negative 3i roots of 5. Plus 2i times negative 4 is negative 8i. And then 2i times negative I roots of 5 will be negative 2i squared roots of 5. So, now let's see, as far as combining like terms, if I can. Technically, this and this are like terms. To combine them, though, because this has a radical, it wouldn't be that friendly. But I can simplify something a little bit further. Recall, earlier on, we had I squared is equal to negative 1. So I can simplify this to negative 12 minus 3i roots of 5. My 3 actually has like a little square root built into it. That's weird. Minus 8i. And this is negative 2 times negative 1. I believe that's plus 2 roots of 5. Am I wrong? I don't think I am. So this actually had become a real number right here. And then I guess I could kind of group all my reals and then imaginary parts together. So I'd have negative 12 plus 2 square roots of 5 is the real part. Pardon me. And then the imaginary part would be negative 3 I roots of 5 minus 8i. Now, if I really, really, really wanted to write it in the form a plus bi, this rectangular form, I could technically write these two in terms of some number times I, and the way I could do that is by factoring out an I. And pardon my cough. So I'd have negative 12 plus 2 roots of 5 minus 3 roots of, well, let's see. Oh, let me factor out a negative I just to make things a little bit easier, since both of these are negative. So minus, technically, it'd be I times a set of parentheses. I'm going to do a set of parentheses times I, and I'd have left on the inside 3 roots of 5 and plus 8. The reason this 8 is positive is because I factored out the negative there. So my A would be this whole thing here, and my B would be this whole thing here, technically the negative of that. But I am able to write it in this form if I'm really, really particular about that. So that's how I can multiply these. I just have to FOIL it out, or double distribute, if you will. And then I just want to point out that oftentimes you'll get an I times an I squared, which is equal to positive 1. So you should simplify from there, if possible. And the last type of problem I want to do is division. Let's do one of these real quick. Let's actually talk about the 1 over I that I had earlier. Now, I in a denominator is technically not allowed because I is the square root of negative 1. So, square root of negative 1, right? It's a square root. I don't allow square roots in the denominator. So I'd have to figure out what would I multiply this by in order to get rid of the I in the denominator. And now, if it was just like the square root of something, typically you'd multiply by square root of something over itself, right? However, I like to try to plan what would I multiply it by to get I to the 4th. Multiplying it by something to get I squared would work equally well. As long as I'm left with something that isn't an I in the denominator, I would be fine. So I could multiply by I over I and get a negative, or I could multiply by something that's going to give me I to the 4th, and at least have a positive 1 in the denominator to take care of it in advance. So I'm going to multiply by I cubed over I cubed, and my reason is 1 plus 3 is 4, and I like I to the 4ths, right? So my numerator would be I to the 3rd over I to the 1st times I to the 3rd is I to the 4th, which is 1, and I to the 3rd divided by 1 is just I to the 3rd. So that's kind of nice. Pardon me. So yeah, multiplying our denominators by stuff, that's good stuff. Maybe I'll do one more quick. I'm flying through this video, so I might as well fit one more crazy example in here. What if I've got something like 2I over I to the 5th times the square root of 3? Something ugly. So 2 problems here. I don't like i's in the denominator, and also I don't like square roots in the denominator. So I've got to multiply this by something that's going to get rid of that, and I've got to multiply it something over itself, because that's really 1 there, right? And multiplying by 1 doesn't change the value of the original problem. So I to the 5th, what could I multiply that by in order to get something that's going to be a multiple of 4? Well, it happens to be I to the 3rd again, because that'll give us I to the 8th, which is a multiple of 4. And square root of 3, what could I multiply that by to get rid of the radical in the denominator? Well, square root of 3 would be nice, because root 3 times root 3 is root 3 all squared, and the square and the square root would cancel out. So that would work out quite nicely. So let's multiply this. 2 I times I cubed is I to the 4th. Man, I didn't realize I was going to have so many I to the 4th, so that's fine. Times the square root of 3 is my numerator. I to the 5th times I to the 3rd is I to the 8th, which I'll be able to simplify. Root 3 times root 3 is square root of 9, which is 3, or just root 3 squared, which is 3. Whichever way I look at it, it is 3. Let's see, so I to the 4th is 1, so that's just 2 square roots of 3 up top. I to the 8th, I could think of as I to the 4th all squared, right? Which is 1 squared, which is 1. I don't think you need to write that much work. It's 1 equals 3. And now I just want to point out I can't cancel this 3 and this 3, even though you might want to, because one is in a radical and one is not. And even if they were both in radicals, if the indexes of those radicals didn't match, you couldn't reduce those either. So my answer actually happened to be a real number. Once again, like I said, operations on the complex set of numbers are not closed. It's possible to get something that is also not complex. And then last type of example, as far as simplifying, what if I've got 3 minus I divided by, let's do, I don't know, 2 square roots of 3 plus I. So you might not see much of a problem here at first, but let's write this as a fraction, and then I think the problem will reveal itself. So when I write this as a fraction, it's more apparent to me that I've got two issues. One, I've got a square root in the denominator, and I've got an I in the denominator, which is a type of square root. And I want to multiply by something, but I can't just multiply by like this or something like that, because that actually won't deal with this properly. Because it would get rid of the square root of 3 in this term, but then it would introduce an I. It would get rid of the I in this term, but then it would introduce the square root of 3, and I'd kind of have some weird switcheroo situation, which wouldn't be helpful. The way you deal with this is by using a convenient little trick. I'm going to use the sum and difference pattern, which is equal to a squared minus b squared. And so these two things are called conjugates of one another. They are not opposites. Conjugates. Why? Because they're not entirely opposite. If they were, the a would have been negative over here as well. It's just the middle signs that are different, okay? So, and if I multiply by the conjugate, I get the difference of squares property, or pattern, sorry, which helps us because if I have this term squared and the I squared, both of those will be something that gets rid of those roots in the denominator. So, let's multiply by 2 roots of 3 minus I over 2 roots of 3 minus I. And once again, this is called a conjugate. Conjugate. Which just is a word that means pair, like a pair of things, right? So be careful here. When I multiply these numerators, the vinculums are grouping symbols. They suggest that these are parenthesized, if you will. And I have to distribute this properly, so be aware of that. A lot of people won't distribute correctly when doing something like that because they didn't spot the grouping symbol. So be careful. So let's see, 3 times 2 roots of 3 is 6 roots of 3. 3 times negative I is minus 3. Negative I times 2 roots of 3 is negative 2I roots of 3. And negative I times negative I is positive I squared. Won't be positive for long, though, if you know what I'm saying. It's going to be negative. And then the denominators, I could FOIL it out like that, but better yet, let's just use the pattern. By the way, in this pattern, the middle sign is always negative. So I'll have 2 roots of 3 all squared minus I squared, right? So let's keep simplifying here. Let's see, so I squared, like I said a moment ago, is going to be negative. So I'll have 6 square roots of 3. These are technically like terms. I could do my weird steps with it like I did in one of the previous problems, but I'm not going to bother this time. And plus negative 1, which is just minus 1. All over, 2 squared is 4, root 3 squared is 3, minus I squared is negative 1 again. So I'm just going to bring my kind of constants together. 6 roots of 3 minus 1, minus 3I minus 2I rad 3. All over 4 times 3 is 12, plus 1 is 13. And then if possible, if for some reason each of these terms was divisible by 13 in some capacity, I would simplify it, but in this case, I will not. So that is our 19-minute review of how to simplify complex numbers. We used to spend 3 separate sections on this in a previous course, but like I said, it's review. And like I said, also, feel free to go back and look at some other videos of mine. I have other examples that goes through this more slowly if you would like. So thanks for watching, and have a great